Hello, I am Sang Shin, a master's student at Songyungan University. Today in this video, I would like to present about the paper titled One-Shot Imitation in a Non-Stationary Environment via Multi-Modal Skill, which was published at the last ICML. Before that, let me introduce our lab. Our lab is led by Professor Hong-Wook Woo, and we mainly research reinforcement learning, RL. Our research encompasses multitask RL and meta RL aimed at rapid adaptation to a variety of tasks. We also focus on sample efficient offline RL for efficient agent training with limited data. Also, we study multimodal reinforcement learning to utilize diverse data types like video and language, and skill-based RL focusing on simplifying and solving complex tasks by dividing them into achievable skills. The conference where this paper was published, known as ICML or the International Conference on Machine Learning, is one of the most prestigious conferences in the field of machine learning. Our work aims to solve the one-shot imitation problem in a non-stationary environment. One-shot imitation refers to learning from a single expert video demonstration. A non-stationary environment means the environment where the underlying dynamics changes over time. For example, an environment where the direction and strength of the wind changes every single time step. The goal of this study is to train an agent capable of performing one-shot imitation in a non-stationary environment, which we've termed one-shot imitation and zero-shot adaptation. Therefore, the agent is expected not only to learn from a one-shot demonstration, but also to adapt to unseen non-stationary dynamics. During the phase where the agent is being trained, we assume complete ignorance of the non-stationarity of the target environment. This means we are making a very practical assumption that the environment where the agent is trained is different from the target environment. To address this problem, we have developed a framework called ONIS, which stands for One-Shot Imitation Learning Framework using semantic skills. The methodology involves disentangling task and dynamics related features. Let's take a closer look at what this means. Task refers to the actions the agent must perform. Since the task to be imitated is determined through a video, we utilize a pre-trained vision language model to extract task-related features or semantic skills from the video demonstration. Semantic skills are expert behavior patterns associated with language instructions. For example, actions like open the drawer or grab the ball can be considered semantic skills. Essentially, semantic skills are the agent's short horizon actions that can be expressed linguistically. Next, once the task to be imitated is determined, it needs to be executed in a non-stationary environment. However, since the dynamics features of the environment change, we identify these features through a dynamics encoder. We base the training of dynamics encoder on contrastive learning, where the input to the dynamics encoder is a state action subtrajectory and the output is the dynamics feature. The semantic skill extracted by the vision language model and the dynamics feature extracted by the dynamics encoder combine to represent a dynamics-aware skill. By sequentially executing these skills, the agent can imitate complex tasks given in a video within unseen non-stationary environments. Executing each skill means that there is an action decoder for the linguistically expressed semantic skill, which decodes the primitive action sequence appropriate for the environment's action space. Through this process, we enable one-shot imitation and zero-shot adaptation, as previously mentioned. Let me explain the methodology in more detail. First, the semantic skill encoder is a module that watches a video and extracts semantic skills. In other words, the input is the video and the output is a sequence of semantic skills depicted in the video. For example, the output of this module could be a sequence expressed in text form, such as close drawer, push button, and so on. In this context, each instance of close drawer is a semantic skill present in the video demonstration. The semantic skill encoder is developed by applying prompt learning to a pre-trained vision language model, or VLM. Notably, we utilized CLIP, the state-of-the-art multimodal model available at the time of this paper's publication. The CLIP model is trained to map objects and their textual labels into the same embedding space, enhancing the sample efficiency of learning when this pre-training approach is combined with prompt learning. Prompt learning involves adding a small number of learnable parameters, referred to as prompt, to the front end of the multimodal model's language encoder, typically implemented in a transformer architecture. This allows for parameter-efficient learning without the need to adjust the entire set of pre-trained parameters. In the diagram, the prompt theta p, depicted in green, is the only parameter that is learned, leaving the pre-trained video and language encoders without additional parameter updates. The loss function used for prompt learning is a classification loss. Specifically, we input a video clip of frame length h into the VLM clip and prompt it to predict the semantic skill depicted in the video clip. Once the semantic skill encoder is trained in the manner described earlier, it produces a sequence of skills contained within the video. This is achieved by moving a sliding window across frames to predict semantic skills, resulting in the prediction of skills from Z0 to ZK in the figure. For example, Z0 could be close drawer and ZK might be push button. After extracting such a skill sequence, the semantic skill decoder then predicts whether the skill being imitated has concluded. In other words, it determines the moment when the imitation of Z0 is complete. Since the semantic skill decoder receives the semantic skill expressed as a text embedding as input, it does not require a vision input and thus has been implemented using a basic multi-layer perceptron. Specifically, it performs binary classification to determine whether the semantic skill ZT has ended and if ZT plus 1 should be executed next based on the inputs, which are current semantic skill ZT the current state st, and the initial state st0 at the beginning of the skill execution. The previous section detailed the process of extracting task information to be performed from a video. Now, we turn to predicting environmental features to adapt to the environment. The model for predicting these features is the dynamics encoder. The input to the dynamics encoder is the state action sub-trajectory from an expert demonstration, and its output is the environmental dynamics feature. Because it receives input that includes information on length, the dynamics encoder has been specifically implemented using a transformer architecture. Just as a transformer can accept varying lengths of text embeddings as input, this dynamics encoder is designed to take in state action sequences of varying lengths as its input. This approach allows the encoder to effectively process and learn from the temporal dynamics present in different lengths of state action trajectories. The training loss for dynamics encoder comprises two main components. The first is an objective function for reconstructing the input state action sequence through a dynamics decoder. This approach mirrors the learning method of auto-encoding models, where the goal is to reconstruct its own input accurately. This is aimed at embedding a unique representation of the subtrajectory into the embedding space. The second component involves learning through contrastive learning. In contrastive learning, the concepts of positive and negative pairs are important. Positive pairs are trained to remain close to each other in the embedding space, while negative pairs are trained to be farther apart. For training our dynamics encoder, sub-trajectories from the same trajectory are defined as positive pairs. This method helps in learning representations that are discriminative for the dynamics of the environment, facilitating the agent's ability to adapt to varying conditions by recognizing similarities and differences in environmental dynamics. The reason for employing contrastive learning stems from the fact that task-relevant features are extracted beforehand by the semantic skill sequence encoder. Therefore, we aim to ensure a close proximity of sub-trajectories in the embedding space if they originate from the same dynamics, regardless of the specific skills involved in the sub-trajectories. For instance, let's consider a dataset containing a single trajectory that includes state action sub-trajectories for two different skills, close drawer and push button. Typically, these two trajectories would maintain a considerable distance in the embedding space due to their distinct state action distributions. However, since they are part of the same trajectory and thus share the same dynamics, we want their embeddings to remain close to each other. This desire to keep embeddings of sub-trajectories from the same trajectory closely aligned in the embedding space is precisely why we define sub-trajectories from the same trajectory to be positive pair. To evaluate our framework, we created an environment called Multi-Stage Meta World. This environment is an adaptation of the well-known benchmark Meta World, and we created the multi-stage version for two main purposes. The first is to measure performance in long horizon imitation tasks, and the second is to implement a non-stationary environment. In the evaluation phase, subtasks like slide puck, push button, etc. must be correctly achieved in the order given in the video demonstration. To emulate a non-stationary environment, we introduce time-varying parameters of the robot arm. Roughly speaking, if the agent predicts action AT, the environment yields the next state according to AT plus WT, where the WT can be thought of as wind blowing within the environment that is not observable to the agent. This dynamic simulates the challenges of adapting to unseen changes in the environment, testing the agent's ability to perform under varying dynamics conditions. Firstly, our skill-based approach demonstrates robust performance in long-horizon imitation tasks. While other baselines adopt a method of imitating a video containing multiple skills in one go, our framework focuses on imitation at the skill level, resulting in a significantly higher success rate for each skill. In the table, K represents the number of subtasks within the video demonstration that the agent needs to imitate. As observed, our framework outperforms the most competitive baseline by up to 54%. This shows our framework's effectiveness in accurately imitating a complex tasks by breaking them down into more manageable individual skills. Moreover, through the contrastively learned dynamics encoder, our framework demonstrates robust performance against unseen non-stationary dynamics. While the performance drop in non-stationary environments compared to stationary ones for the baseline was as high as 57%, our framework only saw a decrease of 18%. Furthermore, through the evaluation study, the contrastively trained dynamics encoder improves the performance by 20% in average success rate compared to the dynamics encoder trained without contrastive learning. And finally, leveraging the characteristic of our framework to retrieve semantics from the video demonstration, we demonstrated consistent performance across multimodal demonstrations. While the baseline BCZ experienced a 16% performance decrease with video demonstrations, our framework only had a 3% drop in performance. This highlights our framework's ability to effectively interpret and utilize the semantic information from video demonstration. Thank you for listening to my presentation.